give a round of thanks or something like that. You interrupt whenever you want to ask a question. Things like that. I encourage all of you to continue that even here. Feel free to stop me at any point and raise anything, right? Any point that you feel is relevant. Yeah. So I chose the four-color theorem. The four-color theorem is a very popular mathematical result that is among those class of theorems that you can skate so easily, even to a school child, and they can not only understand it, they can even make some progress towards it. And yet the actual solution would be very difficult, much like Fermat's last theorem. Let's say Fermat's last theorem is also of similar nature. It's almost a trinket, a puzzle, right? Find all n such that is there any solution for n greater than 2 to the equation x to the n plus y to the n equal to z to the n, that x, y, z are taken to be positive integers. Very easy to state. Obviously, for n equal to 2, you have infinitely many because you have so many Pythagorean triples, so many right angle triangles. But it's not there. It's not true for n greater than 2. It's not, no joke to prove it. This is something of that kind. The four-color theorem very roughly says, suppose you have a map of the world, okay? But not our world, because our world is a little messy. There are lots of water bodies. Some countries are in various pieces here and there. So many islands and stuff like that. So no, it's a very simple world. We just think of a sphere which are split into certain connected regions, some finitely many connected regions. Okay, each region you can call it a country, and you're interested in coloring this map of the world. And any reasonable coloring of the map will be such that you don't want to give the same color to two adjacent regions. Any map that you see, you want to give different colors to adjacent regions, right? So the four-color theorem is like this. You make a map of the world with the following property, that any one country is not in two disjoint pieces. Okay. So the countries are are not in disjoint pieces, and two countries are adjacent if they share some edge between them. Not just a point. They must share some continuous edge between them. Then we say that the two countries are adjacent. If some countries meet at a point only, then you don't say that they're adjacent. With such a map, how many colors do you need to color it in such a way that adjacent countries don't receive the same color? Fairly straightforward problem. A coloring book problem, which really you should be able to tell it to even a high school student. And you can try out various examples. Draw some squiggly shapes of your own and check how many colors do you need. It will turn out, if you're clever enough, you can always perform a coloring with not more than 4 colors. Sometimes fewer, but not more than 4 colors. Okay. And this was first observed in sometime in the 1850s, 1852, I suppose, by a certain fellow called Francis Guthrie. It was either Francis or his brother Frederick. I'm not sure which one. Some F. Guthrie. Okay. So Francis Guthrie, let's assume it's Francis for the purpose of this talk. So Francis Guthrie posed this question to his teacher. He was a student of mathematics or something in England. He posed it to his teacher, De Morgan. De Morgan, I'm sure many of you have heard of through De Morgan's laws. Small request, if it's convenient for you, please feel free to switch on your videos also, because while I'm talking like this, at least I feel a little bit better if I can see someone's face. Otherwise, it gets a little bit difficult. I don't know whether anything I'm saying is having any impact or not.
Yeah, sure.
But only if you're comfortable. I'm not insisting. And besides, there's all this bandwidth problem and all that you all have to take care of. I completely understand that it's easier said than done. Yes. Okay, so anyway, yeah. So as I was telling about the story, so Sneha's here. I did not see your name earlier. How are you doing?
I'm good. I'm just
Good.
listening.
Uh-huh. Very nice. Lovely. So, so Francis Guthrie, as a student, posed it to his teacher, De Morgan. He said, "Look, my brother claims that four colors sometimes are necessary, and it seems that no matter what he tries, you don't need more than four. Is there any way to prove this?" So De Morgan takes a look at it and he says, "Yeah, that does seem to be true, but I have absolutely no idea how to prove it. Let me take a look at it." So De Morgan takes an interest in it, and he goes around publicizing it everywhere. He in writing, in lectures, and things like that. So this way, the four-color theorem gains a lot of four-color conjecture, I should say, gains a lot of notoriety. So he writes to Hamilton, for instance. Hamilton, I'm sure many of you have heard. I don't know if you've taken linear algebra. Physics people surely would have heard of Hamilton. It's quarter nines and things like that. So, De Morgan writes to Hamilton and says, "Look, here's a problem which I do not know how to solve. What do you think about it?" Hamilton is like, "Mere ko kuch nahi. I am not interested in this problem." So he drops it, but still other people take interest. And sometime around in the 1880s, I believe 1880 itself, uh, a barrister by the name of Kemp, okay, he proposes a solution to this problem. And it gets published, and it's vetted by many people, and it gets published, and even on the basis of that, Kemp becomes a fellow of the Royal Society and things like that. So it seems like, okay, he's given a very clever solution and it's settled. Great. Frederick took it to De Morgan. I see. Okay. Yeah, it was either one of those two guys. Francis and Frederick were brothers. Francis and Frederick Guthrie. No, I do not exactly recall who was it. Apparently, it's Frederick. Thank you. So then, when Kempe published his solution, several people said, "Oh, that's great. It's done. It's a very clever one." Some people improved on it. Tate produced another solution, and so on and so forth. And that was the status of the problem in after 1880, when Kemp resolved it. Then, around 10 to 11 years later, another mathematician, English mathematician by the name of Percy Hewood, he shows that Kemp's proof was wrong. A few years later, Peterson shows that Tate's proof was also wrong. So now we're back to square one. So it's one of those rare instances in mathematics where a vetted proof, actually turns out to be incorrect. Okay. Published and vetted by several people, and everyone thinks that it's okay, and somehow it suddenly turns out that it's incorrect. One of the rare instances, which makes it all the more interesting, actually. So that was the status. He would demolish Kemp's proofs, and he proposed certain improvements of it, and it was very valuable to get a deeper understanding of the problem. And such was matters for a long time, that people tried various approaches and they failed, tried various approaches and they failed, tried various approaches and they failed. It's finally settled all the way in 1936. That too by Apple and Hacken and Apple. Apple and Hacken. But interestingly, by computer, which is to say, they figured out that there are only these many number of configurations that you need to check, that you need to test for, to find out whether the Four-Colour theorem is true or not. And they managed to, but it's only these many, meaning only some finitely many. Okay, and so they used a computer to check it out. But this is not the correct context in which you should look at it. The point is, they had to test some around 1,800 configurations. You can't do it by hand. Okay, and they had to code it by computer. And this is 1976. Remember, it's not the computers of today. Okay, so it's in fact the first major theorem in mathematics which was actually verified or proved by computer. So it was a huge shock at that time that here's a very classical theorem which people are taking a lot of interest in, and of all the ways to settle it, it's a brute force calculation, that too done by a computer. It was highly dissatisfying to many mathematicians, who were, who grew up in a certain culture in which a mathematical result is true if you can explain it, to another mathematician. Now, how do you explain, several thousands of lines of computer code to a mathematician and say, this is why it is true? It's aesthetically or culturally unsatisfying. That is what many mathematicians at that time said. Now things have progressed a lot more. Even today, there are some people who might say that, but it's moved on a lot. Computer science has become a great field in itself, especially theoretical computer science. So those kinds of objections are no longer valid. But not only throughout the history of this four-color conjecture to the four-color theorem, it's had all these surprising elements to it, which makes it really interesting. So if this were like I was telling before this, before all of you entered, I was just having a chat with some of the people who were here, Devashish and other people. I was just telling how when we used to run the math club, and actually, you people were in IISER Bhopal, and we used to actually meet physically and have this math club and all. At time we would just go on and on and on with these mathematics. So possibly if I were talking about the four-color theorem live like that in front of you, I would probably take several weeks of continuous math club worth discussions out there in it. But I have only, let's say, only half an hour. So all I'll do to you is I will give you Kemp's proof, the first one, 1880. Okay, very simple and straightforward argument. It's your job to tell me what's wrong with it. Let me do that. Okay, so it's 522. Have a little bit of history of it. Let's get started. Let me see whether it can be done by, let's say, 20 minutes. 20 minutes for campus proof, and then you can tell me what is wrong with it. How does that sound? Let me try and share my screen. Yes, missing e to the I pi plus 1 equals 0. Devashish Samantha is saying. Context behind that is that it was our unofficial motto for the math club. The tradition was whenever you enter the L6, wherever L6 was where you used to meet, right, Devashish?
Yeah, L6. Later on, we
L6.
shifted to some other rooms as well. But
Oh yeah, we moved to the math building
math
at some
building,
point of time. Yeah. At certain point of time, we were in L6 largely. Yeah, so the tradition was you have to get the keys and open the door. Once you open the door, the first thing you print on the board is e to the I pi plus 1 is equal to 0. That was our tradition. So yeah. Let me see. I'm just trying to share my screen. Just hold on for a second. Is the board visible? I hope it's visible. Here we
Yes,
have
sir.
I pi plus 1 is equal to 0 as requested. Right. So Kemp's proof. So there are two elements to Kemp's proof. One is let me see. I've spoken this much. I should probably ask. Does everyone know what a graph is? If there's someone who doesn't know, what a mathematical graph is. There is the notion of graph. You might think, okay, you think of a graph of a function, in which case, y is equal to x squared. It looks like this. No, I'm not talking about that graph. There's a different graph which appears in graph theory. Does everyone know what that is? If there's someone who doesn't know, I mean, if this was Zoom, I could ask you to raise your hand, I suppose. Can you do it here? Oh, you can. That's great. Oh, I see. Okay, so there's at least one person who doesn't know what a graph is. No problem. So I can start with that. Good. Pranam also. Okay, no problem. Good. Right. So a graph for us. A graph G equals V comma E is well, maybe this is not the best way to put it. A graph G is an ordered pair. The mathematical way of putting it, it's an ordered pair V comma E. Such that certain things happen. I really want to go into this. No, let me in the interest of in the spirit of whatever I'm going to do after this, which is to tell you about Kemper's proof, which is obviously going to be very informal, let me tell you what a graph is visually. The following is a graph. A graph is a collection of vertices, okay, and with some edges between them. With some edges between the vertices. This intuitive notion is what we call a graph. Okay. So if you want a picture, I would say, okay, here, for instance, is a graph. Here are some 1, 2, 3, 4, 5, 6, 7 vertices. Following is a graph. Oops. Pretty bad edge. Here you go. So if you want, I can label the vertices 1, 2, 3, 4, 5, 6, 7. And you have edges. So if this is the set of vertices, then I'll say V is the set 1, 2, 3, all the way up to 7. The edge set is 1, 2, 1, 7, 2, 7, 3, 7, 3, 6, 3, 4, 3, 5. So here I'm just using a shorthand. When I say 1, 2, I really mean the set consisting of the elements 1, 2. When I say 3, 7, I mean the set consisting of the elements 3, 7. But I don't want to do too many brackets and all that. Just for convenience, just giving this shorthand, so to speak. Okay. So this is what a graph is. You have some bunch of vertices and you have a bunch of edges between these vertices. That's what a graph is. Okay. Is this much clear? I hope this much is fine. If you have any questions about definition of a graph, just let me know. Feel free to interrupt me at any time. Okay. So the four-color theorem is about planar graphs. Planar graphs are those graphs that can be drawn on a plane. But in what sense? Can be drawn on a plane without intersecting edges, without edges overlapping. Overlapping is probably not the right word. Intersecting is probably the better word. Intersecting each other. At points means, to be more specific, of course, two edges will intersect each other if they share a vertex. So they should not intersect other than at the vertices. Each other at points other than the vertices. Other than the vertices. So this lovely graph that I drew right over here, this is a planar graph. I've drawn it on a plane and the edges are not really intersecting each other. Here, for instance, is an example of okay, so here's the question. Suppose I draw the following graph from here to here, here to here, here to here. Okay, this is drawing on a tablet is not easy. Should have probably prepared these diagrams beforehand. Okay, then you have, let's say, this, and this, and this. Is this fellow a planar graph? Call this fellow G. Is G planar?
No.
Option A, yes. Option B, no. We certainly have one vote for no. Okay. Does anyone want to disagree with that? The definition is right on top. Those graphs that can be drawn on the plane without edges intersecting each other at points other than the vertices. So one confident no is there, no problem. Any other votes either way? Maybe you can put it in the chat if you want. You can take a look. Yeah, says no. Jitesh says no. Lots of no's. Okay, that's very good. Very good. Great. So this example was meant to illustrate a subtle point about the definition. Okay, so this is a drawing of a graph G. Okay, so what is a graph? A graph is this data. Tell me the vertices, tell me which edges are there between which vertices. That's what this graph is. So if I want, I can maybe label this graph also 1, 2, 3, 4, 5. So you know the vertex set and you know the edge set is 1, 3, 1, 4, 2, 4, 2, 5, 3, 5, whatever. Okay, that. So that data is a graph. I have chosen to give a drawing of this graph in this fashion, whatever you see over here. But it is not the only possible drawing of this graph. So it's planar if I can draw it on the plane such that edges do not intersect each other at any point other than the vertices. So can I draw this in such a way? Is there a way of rearranging this drawing so that all these intersections don't just go away? What do you think? Is what I said clear? Is the perspective clear? The data of a graph is what are its vertices? Which edges are there between which vertices? How I draw it is up to me. I have chosen to draw it like this. In this way, obviously there are intersections between certain edges which are not occurring at the vertices. There are extraneous intersections. Can I somehow redraw this graph such that these edges can be, these intersections can be removed?
You can draw that graph, but it won't be on the same plane, right? If you want to remove the intersections.
You want to say, okay, let's try drawing it in 3 dimensions, let's say,
Three
and somehow.
dimensions, so you don't intersect then that, but in a plane you need to intersect it.
Correct. If I draw it in, let's say, a different region, not the plane, I draw it in, let's say, R3, or maybe I draw it on some other surface in R3 or something like that. Maybe it's possible that it's not. But this one, it seems that everyone is convinced that it's not possible to draw it in the plane. So let me kill the suspense and show you that it can be drawn. This is, after all, a cyclic graph. Do you notice? 1 to 3 to 5 to 2 to 4 to 1. It's a cyclic graph. Which means I'll just call it, draw a circle, label them 1, 3, 5, 2, 4, 1. This is the same graph. This is also G. Convinced yet? It's the same graph, huh? Absolutely the same graph. This fellow is also G. Correct answer is yes. I did not mean to trick you. This is meant to illustrate a subtle point in the definition. Okay. Hey, Sneha already suggested that. Good. 1, 3, 5, 2, 4. That indeed gives you that. Excellent. That is exactly what I wanted you to figure out. Good. So when I say planar graph, I mean those graphs that can be drawn in the plane without edges intersecting. Okay. Now, these are the 2 primary definitions. And now let's state the Four-Colour Theorem, just to be sure. Okay. So what does the Four-Colour Theorem say? The vertices of any planar graph can be colored using 4 colors in such a way that adjacent vertices have distinct colors. Now let's see if this makes sense. So a coloring of a vertex is, well, it's what you think it is. You just take some colors and you put them over there. So let's say this is a valid coloring of this graph that I have over here, using 3 colors: red, blue, and yellow. So I'm just taking the vertices, I'm just placing some color on them. Here I've colored 1 and 5 with red, 3 and 2 and 3 with blue, and 4 with yellow. So this is a valid coloring of it's a coloring of this graph. Moreover, this coloring has the property that adjacent vertices which is to say two vertices are adjacent if there is an edge between them. So adjacent vertices do not have the same color. And this is a coloring with that property. I have used 3 colors. This is a planar graph, and I can do it. I have produced a coloring of this graph using less than at most 4 colors, such that adjacent vertices receive different colors. Okay. The claim is that, or the theorem claims that for any planar graph, you can do it. You can do the same thing using 4 colors. Okay. So what relationship does this have with that map coloring thing that I was talking about? Suppose that this is the world, and here's your map. Here are countries. So what's the best way to do this? Let's pick some arbitrary division, right? Something like this. Okay, so here's a bunch of countries. Each of them is a different one, and I want to give some colors to each of these guys. Now I want to translate this problem of coloring these regions, okay, into a problem about coloring the vertices of a graph. So here's what I'm going to do. For every region, that is to say for every country, I'm going to place a vertex. Okay. And whenever 2 countries share an edge, I'm going to draw an edge between the corresponding vertices. So these two guys, these two guys, this fellow, this fellow, this fellow, this fellow, this fellow, this fellow. You see what's going on? Does it make sense? So I unfortunately use the same color for both of them, so now it looks like an absolute mess. I should probably have used a different color for the edges. But I hope the process was clear. That how from given a map of countries, drawn on the sphere or drawn on the plane, you get a corresponding planar graph. And coloring a country with a certain color just corresponds to coloring the corresponding vertex with that color. Okay. So when Francis Guthrie or Frederick Guthrie, and they formulated the Four-Colour Theorem in terms of coloring of maps on surfaces, you can also translate the problem into a graph coloring problem. You color the vertices of a certain planar graph as per satisfying a certain condition. Okay. So is this equivalence also clear? Yeah, I was in too much of a hurry. This would have been cleaner if I'd drawn some other color of the edges. Okay. Seems there's no issue. Good. So here's what the Four-Colour Theorem says. Now, I keep saying that the Four-Colour Theorem says that the Four-Colour Theorem says this, but is it really obvious that even why I see something is there? So you're taking the regions. Yes, you're taking I take the regions as the vertices, and I draw an edge between 2 regions, between 2 vertices, if the corresponding regions share a common border. It shouldn't just share a point as a border. It should share a common line as a border. That's how I'm drawing them out. Good. Excellent. So right. So I keep saying that the Four-Colour Theorem says this, and it's been proved, and there's this whole history behind it. But is it even clear that you can't find a graph with which needs some n colors? Because in fact, this was talked about by Cayley a long time back when this Four-Colour Theorem was doing the rounds, and Cayley also spent some time. Cayley, I'm sure all of you know about through a group theory at least, if not through a linear algebra at least. Okay. Arthur Cayley, very famous and mathematician from England. So, for instance, how can you ensure that 4 colors are necessary? Here is one way to ensure that 4 colors are necessary. Let's draw. So here is this, and there is also, let's say, this. Consider this graph. Okay, so this is a graph on 4 vertices. How many colors are necessary for this? Can we do it with fewer than 4? Suppose I give this a certain color. In fact, let's color this red. Let's say, then it's adjacent to all 3. So a distinct color has to be given to each of the other 3. So let's say we give this blue, but blue, this vertex is also adjacent to all 3, right? So any other color, a third color must also be distinct, but this guy is also adjacent to all 3. So fourth color must be given over here. Okay. So this is an example of a graph which planar graph that needs 4 colors at a minimum, right? In fact, this is also called the complete graph on 4 vertices. So the standard notation for this is K4. This is the complete graph K4. So what do I mean by complete graph Kn? It means you take n vertices and you put all edges between all vertices, right? So that's the case over here. There's an edge between any 2 vertices over here. So it's K4. And K4, as it turns out, is a planar graph. There's a way to draw it. It's possible to give a drawing of it such that no edges are intersecting except at the vertices. So it's a planar graph. In general, of course, Kn, the complete graph on n vertices, will need n colors, because once you color one vertex, it's adjacent to all other n-1 guys. So all the other n-1 guys have to receive, and this is true for whichever vertex you color. So you have to have n colors on Kn. But the thing is, Kn cannot be drawn on the plane for n greater than 4. Just try it and see. Can you draw, let's say, K5 in the plane? Try as you might, I assure you, you will not be able to. So you can't do something clever like how we did with this fellow right here. Okay, if you take K5, then you can't do it. And since K5 is contained in K6 and etc. etc., if you can't do for K5, you can't do for any other Kn. So K4 you can do, but K5 you cannot do. So this neat observation that, if we take a complete graph, then sure, n colors are ensured, doesn't help us to solve the 4-color theorem. Okay, because those graphs for which you do need large number of colors doesn't help us not solve, doesn't help us provide a counterexample to the 4-color theorem. That's what I should really say. Okay. Okay. So there's that. But let's think about this. How should I put this? See, the problem is more complicated than appears at first glance. That's what I'm trying to impress upon you. So the reason for that is, suppose you have some really complicated graph. Okay, you have a whole bunch of vertices and lots of edges between these guys, stuff like that. Okay, so a whole bunch of these guys are there. There's no issue. I'm saying, suppose for instance that you look at the colorings over here along this outermost cycle. Okay, suppose all 4 colors appear over here. Now let me create another planar graph by adding a vertex here and putting in all these edges. This is also a planar graph. But now, since all 4 colors appeared over here, those 4 colors are not valid for this vertex. So 5th color is necessary. Do you get my point? If you have found a coloring of this smaller graph that I started out with, such that the outer cycle took 4 colors. But then now I can create a bigger graph with one more vertex, which is also planar, but which will now need 5 colors, because none of those 4 colors are valid options for this fellow. But the theorem says that 4 is always needed, which means not only can you color the smaller graph using 4 colors, you can always do it in such a way that more stringent conditions are applicable on it. Which is to say, you will never see all 4 colors appear over here. Or you can always recolor this guy, recolor the smaller graph such that 4 colors are not all appearing over there. So that, the larger graph now is has a valid coloring. So it's not so easy. number increase after the graph already becomes non-trivial. Yeah, for Kn, yes. For the complete graph on n vertices, yes. But of course, you can draw many other graphs with more than 4 vertices, which are also planar. That is not an issue. Okay. So, so what I'm trying to impress upon you is that what coloring you start. So it's not a simple inductive process. That, okay, suppose I color all graphs with n vertices, pick n plus 1 vertices. Then by induction we'll do something. It can't be just that easy. Okay, it can't be just that easy because of stuff like this. You have to use some more structure somewhere. Okay, does that help? I don't know. So it's not easy. I don't know whether this is helping out, but let's see. Let's see what Kemp had in mind. Okay, so Kemp's attempted proof of the four-color theorem. So let's just call it FCT of the four-color theorem. Okay. So maybe I should give a small, motivation for why I'm doing this. Okay. Part of it was, of course, that I can't spend 3 hours with you telling all that I want to tell about the four-color theorem. Okay. But the more salient question is, why tell you something which you know is wrong? I mean, what are you going to get out of it? You spent 1 hour today with me and you learned how not to prove the four-color theorem. Is that it? I mean, that can't be it, right? There has to be something more out of it. So sometimes it is true that if you see something which is wrong, a wrong argument, then there is something that you can, something pedagogical, let's say, that you can gain out of it, or you learn about some logical pitfalls. That is another thing. For instance, have all of you seen this proof of 0 equal to 1 and stuff like that by division of, you do some complicated algebra and suddenly 0 is equal to 1. Have you seen these kinds of things before? I hope so. Does anyone not know what I'm talking about? Please feel free to raise your hand. Okay, so right? I mean, you'll do you'll take x is equal to 1, then you'll take x minus x. Then you'll do some complicated thing. Somewhere you'll cancel by x minus x and you'll get 0 equal to 1. So, of course, you're not supposed to do that. You're not supposed to divide by 0. You're not supposed to cancel 0 on both sides of the equation. And this is a pitfall that, you learn. Okay, you're supposed to avoid this. Be aware of such kinds of things. That's one thing. Very related is that it's a very good example. It did not occur to me, but yes, that is also very valid point. Thanks to Devashish Samath in the comments. Points out that yes, a very basic example is what I just gave you, division by 0. Maybe a slightly more complicated example would be you can't take square roots without taking into account that you get a plus minus sign. So there are some external solutions. Using that, you can prove stuff. Again, you can prove stuff like 1 is equal to 0, and half is equal to minus half, things like that. So that is also something to be avoided. But things with depth include something like pointed out by Devashish in the comments, which is, I don't know if you know this, but Fermat's last theorem was also proved and reproved several times over the years. But iota is equal to 1 upon, what's wrong over there? Iota squared is minus 1, right? You say you proved iota is equal to 1 over minus iota. And that is a problem because it's not true. By mistake. Not sure I follow. But let's take it up maybe a little while later. So just to point out what Devashish was saying is that for p equals 23, So there's a very elegant proof of Fermat's last theorem, which involves factorizing over, not over integers. Okay, so you factorize over uh, a ring which is bigger than the integers. So these are rings of integers which contain a pth root of unity. Pth root of unity. Okay. So why would that happen? Because you wanted to solve the equation x to the p plus y to the p equal to z to the p, right? So you factorize x to the p plus y to the p using pth roots of unity as x plus y into x to the p minus 1 plus some pth root of unity times something. So you do a factorization like that and some basic algebra, and you can prove Fermat's last theorem. And this is a very fascinating place in the history of mathematics where this proof of Fermat's last theorem fails for a very weird reason, which is that you cannot uniquely factorize if you generalize to these rings which are not the integers. And then a whole bunch of theory developed out of this and led to the field of algebraic number theory, class field theory. Oh my God, it just goes on and on. Okay, so that's a non-trivial example. Here is also somewhat non-trivial example. So Kemp's proof is false, assured. It's also slightly subtle. Okay, but there are things of value you can take out of it. Okay, and that is the concept of a Kemp chain. Okay, which you will see very shortly. Okay, and this notion of a Kemp chain is very useful and has been applied repeatedly in other areas, even in attempts to prove the Four-Colour Theorem, more sophisticated attempts. But that is something that you can really take out of this. And so let me. So that's if nothing else, I wanted to take away what a Kemp chain is and what it can do for you. Okay, so let's see. Let me go back to sharing my screen. Right. Okay, so the first ingredient is something called Euler's theorem. Does anyone know Euler's theorem? This is not the complex analysis one, not the one that I printed on the first page. Okay, this is v minus e plus f is equal to 2. Has everyone seen this? No. So this is the statement that if you take a planar graph, okay, a planar graph, and let capital V be the number of edges, number of vertices of the graph, capital E be the number of edges, capital F be the number of faces. You know what a face is, right? So let's not get into a formal definition of what a face should be, but if I give you a graph, you can count the number of faces. Then you compute this quantity. It is always 2, regardless of which planar graph you pick. This is Euler's theorem. I hope some of you have seen this. If you have not, do go back and let's say Google it, check out what Wikipedia has to say about it. It's a beautiful, one of the first examples of a topological invariant. Topological invariant. Invariant meaning it's not going to change. It's determined by the topology of the space on which you're working on. Which is to say, on the plane, this is always 2. Okay, so that's the beautiful thing about this. So we will use Euler's theorem to identify a certain property about planar graphs. Okay? And secondly, we will introduce this notion of Kemp, which is called Kemp chain. Okay. So I will not prove Euler's theorem, but we will use it in the following way. So let me also define the degree of a vertex. The degree of a vertex V in a graph is the number of edges incident at V. We usually denoted D of V or something like that. So we usually denoted D of V, degree of V. Okay, so that's what the degree is. We just count for a vertex V, how many edges are there incident of that vertex. That's the degree. Okay, so just keep Euler's theorem in your mind. So here's the first claim. The claim is that if you have a connected planar graph, so connected, again, I'm not going to the formal definition or anything. It should be in one piece. You don't want disjoint pieces, because if you have disjoint pieces, let's just color each of the disjoint pieces independently. It doesn't really matter. So it suffices to just consider connected pieces. So let's look at a connected planar graph. For connected planar graph, there is always a vertex of degree less than 6. This is the claim. And this
Bhaiya,
we
can
can
you
show.
say, hello? Bhaiya,
Yeah,
can
tell
you
me.
say what is connected planar graph again?
Connected. So by connected, what I mean is my graph doesn't look like this. That okay, I have some pieces here, some graph like this, and like this also. So this whole thing, if I call it as the graph G, then no, this is disconnected. This is not connected. Do you get what I'm saying? Is the intuitive picture clear? If you want, between any two vertices, there is some path. Okay.
Okay. Yeah.
Yeah. So this is in two pieces.
So can you repeat it again?
Do you agree that this graph is sitting in two pieces? I'm not saying this is one graph and this is another graph. I'm saying this whole thing is one graph.
Okay.
Okay. Then it's not connected. This fellow is not connected. Right? It's not connected because you have one piece here, you have another piece here, where piece is very intuitive. If you want something slightly more formal, you can, between any two vertices, there is some path. Then it will be connected. But here that is not the case. Between this vertex and this vertex, where is the path? There is no path, no? How do you go from here to there? Okay? Does
Okay.
that make sense?
Yes.
Good. So the claim is that if you take any planar graph which is connected, you can always find a vertex of degree less than 6. Okay, so let's see why. First of all, it suffices to look at maximal connected planar graphs, which is to say, you put in all possible edges. So for instance, over here, I can put in this edge, I can put in various other edges also, I can put in this edge, I can put in this edge. This is not going to change the fact that it's planar. All that you're doing is you're embedding it in a graph for which every face is a triangle. Okay, so let me so proof of the lemma which we have on the previous page. Step 1, it suffices to assume that every face is a triangle. Triangle is a very loose term. The degree of every face is 3. It's bounded by 3 edges. Okay, so why does it suffice? Because if your graph has a face which is not a triangle, you can triangulate that face. Right? So for instance, if let's say this is a face of the graph and there are some other edges going like this, I don't really care. So this is some face of the graph G that they're starting out with. You can triangulate this face. No? After triangulating, what's going to happen to the degree at every vertex? It's only going to increase or remain the same. So if after triangulating all the faces, you can still prove that there is always a vertex of degree less than 6, then even in the original graph, there will always be a vertex of degree less than 6. Is this argument clear? It suffices to triangulate every face and then do it, because in the process of triangulation, the degree will either remain the same or increase. So if for this maximal planar graph, there is always a vertex of degree less than 6, even in the original guy, there is a vertex of degree less than 6. Okay, so that's the argument. Let me know if you want me to go over this again. So that's step 1. So let's assume that every face is a triangle. But if every face is a triangle, then we can make a simple count between faces and edges. So for every face, I'm going to count 3 edges. So as I sum over all, so each time I pick a face, I'm going to count 3 edges. So, but I'm also double counting every edge, because one edge is an edge of 2 faces, one lying on either side. So there are two aspects here. If I have a face, then because it's triangulated, for every face F, there are 3 edges that I'm going to count, E1, E2, E3. But also if I have an edge E, then it belongs to 2 faces. F1 and F2, right? So what I'm saying is, as I count over all faces, so the capital F that I said, the total number of faces, also counts 3 times the number of edges except double counted. So 2F is equal to 3E, or F is equal to 3E by 2. That's I think the correct way to say what I said. Yeah? Do you get what I'm saying? As I've counted over each face, I've actually counted 3 times the number of edges. Am I making sense? But I've double
Yes,
counted
yes.
this twice. Yeah? Does it make sense? So
Yeah.
this is true for our graph. Okay. Yeah, good. Okay. No, it's the other way around, right? So for each F, I'm counting. So each face counts 3 edges. So as I counted over every face, 3 times that number gives me the number of edges. Obviously, I have made some error over here. It has to be the other way around, right? Let me say this again, just so that I don't, convince you by the force of my conviction. Okay. Each time I pick a face, I'm counting 3 edges. So once I've counted every face, how many edges do I have? Well, to count the total number of edges, I count as many faces as there are and multiply it by 3. Count the total number of edges. Count the total number of edges. Just see how many faces are there and multiply it by 3. Because for each face, there are 3 edges. So that's 3 times F. But this is double counting every edge. By saying 3F, I've actually double counted every edge by this argument. So that's 2E is 3F. Never say yes just because someone is convinced that they're right. Some basic algebra will always go wrong somewhere like this. Okay. Kemp might have done this. Anyway, so is this clear? I want to count the total number of edges. If you want to do that, just see for every face, I'm going to count 3 times. So 3 times, so that will give me the number of edges. So 3 times F will give me the total number of edges, but count it twice. I hope this is fine.
No. Can you explain it again? I got confused.
Yeah, I understand. No problem. So, what's the best way to put this? What I want is a count of E. E is sum over all edges in the in the edge set of G. For each edge, you're counting 1. Right? That's what E is. Okay, so maybe this is also not a good idea. Let me change track. Why would I think that for someone who's not getting the intuition, more symbols is going to help? I'm sorry. It's not a good idea. It's like this one. See, you want to count how many edges are there. That total number of edges is the number that I'm calling capital E. Okay, capital E is the count of totally how many edges are there. So how am I going to count it? I can, for each edge, I'll say 1, 1, 1, and I will count. Or there's a neater way to do it, which is for each face, I will say 3, 3, 3.
Okay.
Makes sense? For each face that I see, I will count 3, 3, 3, 3, 3, because each face is bounded by 3 edges. So 3, 3, 3, 3, how many times I want to say? Capital F number of times. That will give me the total number of edges. Yes? So my claim is E is equal to 3F, step 1, but actually not really. In this process of saying 3, 3, 3, 3, which all edges am I counting? I'm counting all the edges which appear, as the boundary of some face. But each edge appears as the boundary for 2 faces. So in the process, let's say I pick F1. So F1 is counting E1, E2, E3. Then F2 is counting E4, E5, E6. Then F3 is counting maybe E1, E7, E8. Yeah, because E1 can appear 2 times. It's bounding F1 and F3 like that. So in this process, if I list down all the edges I've counted, each EI will appear 2 times. Once for Fi, once for Fj, something like that. Does that make sense? So the total count is 3 times
no.
F. the total count for, so if I list down, if this is also not clear, no problem. We'll try doing it like this. Make a list in which for each f1 we list which are the edges which appear there, e1, e2, e3, let's say. For f2, list which edges appear. For f3, list which edges appear. Okay, is that fine?
Yes.
Okay, so the point is, for pick an edge ei, how many times will it appear in this list, in this column? How many times will a given edge appear in this column? Only 2 times. Because every edge will bound exactly, will be on the boundary of exactly 2 faces.
Okay.
Yeah, so it's going to appear exactly twice.
Okay.
Okay, so if you sum over the number of elements in this column, how many are there? 2e. Every edge is there because every edge is on the boundary of some face.
Okay, sir. I got it. I got
Got
it.
it? Every edge is on the boundary of some face. So the total count of this column is 2e.
Okay.
Total count of this
I
column
got
is
the whole point. Okay.
f.
Thank you.
Yeah, you got it. Good. Yeah, good. If it's not clear for anyone else, again, feel free to stop me and ensure that I say it properly. Okay. Okay, does this make sense? Let me just wait for a minute. If it's not clear, or if you want to think about this some more, please take your time. No problem. Okay, fine. So on the one hand, we have v minus e plus f is equal to 2, thanks to Euler. We also have f is equal to 2/3 e. Okay, that's what we have out here. Right. F is 2/3 e. Plugging it back in, what do we get? V minus e plus 2/3 e. That is v minus 1/3 e is 2. So take e to one side and everything else to the other side. V minus 1/3 e is 2, which implies e is equal to, just tell me if I'm doing the algebra correctly, v minus 2 into 3. So that's 3v minus 6. Okay, I think I got it right this time. Okay, so e is equal to 3v minus 6. So here is the relationship between the number of edges and number of vertices of a maximal connected planar graph. Okay, so far so good. So how does this help us in deciding whether there is a vertex of degree less than 6? A very important principle. Okay, is going to appear over here, which is worth remembering for everyone. Okay, and that is, if the average of certain number of quantities is less than something, let's say k, if the average of certain numbers of certain some numbers is less than k, then at least one of the quantities has to be less than k. Okay, sounds really silly when you say it like this, but this is very important. Okay, that's exactly what I'm going to do now. I'm going to compute what will be the average degree of a vertex. So I told you what the degree of a vertex is. Degree of a vertex is nothing but how many edges are incident at a vertex V. So what will be the average degree?
3.
V minus 1.
No, in terms of a formula, let's say, in terms of a formula, what will the average degree be? So for a vertex, it is, you look at how many edges are there and incident over there, and that is the degree of that vertex. But what is the average degree? Well, each edge contributes to, so it's, let me put it like this and ask you whether it makes sense. So the average degree is 2e by v. Does this formula make sense to you? In the sense that, is this the right quantity to count? Because So yeah, if it's not intuitively obvious, somehow I also get stuck like this. So it's like this. When you're talking about the average of the degrees, basically you want to sum over all the degrees and divide by the total number of quantities you're summing over. That's the fundamental notion of average. So what does degree count? What is the degree of a vertex count? The number of edges incident over there. So if you sum over all vertices, the number of edges incident at that vertex, you're counting twice the total number of edges, because every edge has two vertices to which it is incident to. Can you guys see me when my screen is being shared? I'm waving my hands around so much. I don't know whether you can even see me. It's just my voice somehow doesn't make sense. Does it make sense? You want to look at the average degree, which is to say you sum over all the degrees over all vertices divided by total number of quantities you're summing over, which is V, right? So what is the degree of a given arbitrary vertex count? Number of edges incident over here. So as you sum over all degrees, what are you really summing over? How many edges are incident at each vertex? How many are there? Twice the total number, because each edge is going to be counted again in two places. Once for the vertex at this end of the edge and once for the vertex at that end of the edge. Okay?
Yes, got it.
Right? Some people seem to have got it. किसी को नहीं आया समझ में तो बताओ यार, कि चुप मत बैठो. Okay, so seems that it's fine. Good. Right. So if that's your average, you counted the total number, sum of the degrees divided by size of the vertex set. This is the average degree. Then what does this formula say? Right over here. What does it say about the average degree? The average degree according to this guy is 6v minus 12. Then I divide by v. So it's 6 minus 12 by v. That's the average degree. Now here I have to notice v is at least 1. Okay. I mean, of course, 1 doesn't make any sense, but how many? Assuming there are at least 3 or 4 vertices which you have in your graph. If you don't have at least 3 vertices, then you don't even have one legitimate face. Okay, so v is at least 3, which means this guy is at most 6, strictly less than 6, not at most 6. It is strictly less than 6. So here's the principle that I was telling you about, which is extremely important. If the average is less than 6, one of the quantities that you summed over, one of those guys that you're taking the average over is less than 6. Therefore, in particular, there is a vertex with degree strictly less than 6. Okay, so very important principle. So might seem like a silly thing that I'm continuously saying is a very important principle, but you will not believe how useful this is in giving such what do you call it, probabilistic arguments. Okay, so this is something worth keeping in mind. So far so good. There is definitely some vertex with degree less than 6. So the options are 2, 3, 4, 5, whatever, but not 6. So there is, I'm not saying every vertex has degree less than 6. I'm saying there is some vertex, at least one, guaranteed, for which the degree is less than 6. So now that was part 1. Part 2 is Kempe's chain, which I said was extremely important. So it looks like I'm already overshooting the time by quite a bit. So I will try and not make you suffer a lot. I promise you, it's not long. Okay, so part 2. So this is the method of Kemp chains. Right. Okay, so now we found out that there is definitely a vertex of degree less than 6. Let's see what we can do with that information. Kemp's idea was to use the strong induction. So proof by strong induction. So I hope everyone knows what induction and strong induction are. If someone is not familiar, or maybe you know it but you don't know what these terms are, then just let me know.
Sir, I know induction, sir, but what does the word strong signify just before of it?
So induction, as you know it, is the following algorithm. Let's say, yeah, that you prove a certain statement which is claimed to be true for all natural numbers n. Okay, in the following way, that you say you demonstrate that it is true for the base case n equals the lowest, n is equal to 0. Let's say, and then you prove that if it is true for a certain n, then it is also true for n plus 1. If the given statement is true at the value n, then it is also true at the value n plus 1. Then the principle of induction says that you have in fact proved it for all n. That's induction. Yeah. So this is the induction I hope.
Yes, sir.
Right. So strong induction says the following. Base case remains the same, that you indeed have to demonstrate that the base case is true. The induction hypothesis, suppose it is true for all 0 up to n, then it is true for n plus 1. Okay, so you take as the induction hypothesis that the given statement is true not just for n. You take as induction hypothesis that the given statement is true for all values from 0, 1, 2, 3, all the way up to n. And then under this hypothesis, you prove that it is also true for n plus 1. Whereas in usual induction, you just assume the truth of the statement at n, and then using that you prove that it is true at n plus 1. Here you assume the truth for everything less than or equal to n, and then using that you prove at n plus 1. That is why it's strong induction. Okay.
Yeah, sir. Okay.
Any questions? You feel free to let me know. Okay. So Kemp's idea was you prove it via strong induction. So for graphs with 4 vertices, then you can certainly do this, no problem. So that's our base case. And here's what why 4? Because even if you take 1, 2, 3, 4, it's literally obvious, because you're saying you need at most 4 colors, and your number of vertices is less than or equal to 4. Then definitely you can color it using at most 4 colors. So that's not an issue. So n equals 1, 2, 3, and 4. It's already done. No issues at all. Okay. What about so n equals 5 and onwards is something you have to see. So here is this method. We know that there is a vertex of degree. There is a vertex. So now we are taking a graph, which again we can assume is connected. We can assume it's maximal, because maximal in the sense that all faces are triangles. Because if you can do it for that graph, you can do it for any subgraph of that also by deleting some edges. So we know that there's a vertex V with degree of V less than 6. Okay. So let's say this is V. This is V and its degree is less than 6. Suppose it has degree less than 5, less than 4. So suppose there are only 3 edges going out from V. So this is V. Say there are 3 edges going. Okay. Suppose. So there are some more edges over here. Let's say some over here, something like that. But V has only 3 edges going out. So if this is the case, 3 or 2, whichever you prefer, if it's less than 4, then first delete V and any incident edges, which in this case are these 3 guys, E1, E2, E3, if you want, E1, E2, E3. Then color the smaller graph using induction. Okay, this we can do using 4 colors. How? Simply by induction. Once you've deleted V, we get a smaller graph. So that by induction, we know we can color using 4 colors. So do that. Now you have to put back V. So once you have So it's suffice to assume that there are some colors. Let's say there's a color over here, there's a color over here, there's a color over here. Okay, right? So now you put back V. Is it now possible to give a color for V? The answer is yes, because there are less than 4 vertices to which it is incident. So definitely at least one color is left over for V. At most 3 have been used up. So in this case, in this specific case that I'm looking at, exactly 3 have been used up. So there is one color left over, you can color it. So you're done. Color V using the leftover color, or any leftover color. So this takes care of the case when degree of V is less than 4. Okay. Is this case clear? I'm now going to look at the case degree of V is equal to 4, and I will introduce this notion of chem chain. Then I will look at the case degree of V is equal to 5.
So can you just repeat what was the induction?
So maybe that's a good idea to, in fact, place the induction statement somewhere reasonable. So let me just place it over here. So let's take as induction hypothesis. All graphs, all connected inner graphs. But why connected? We can just take all graphs. No? Right. All graphs with number of vertices less than or equal to n for some n, okay, are 4-colorable as per the theorem. This is our induction hypothesis. Okay.
Okay.
So assume this hypothesis and assume now that, or let G, no, let G be a graph with n plus 1 vertices. Vertices, planar graph with n plus 1 vertices. This is our setup. This is our induction hypothesis. This is our this is what we will assume, and what we will try to prove is that for G, the four-color theorem is true. Okay. Once again, we can assume that all faces are triangles. We can assume that what else do you want? You can assume it's connected, things like that. So connected, maximum. Okay, so that's our induction hypothesis, and the case when degree of V is less than 4 is easily taken care of, because if it's less than 4, delete the vertex. You have a graph on n vertices that you can color using the induction hypothesis. But now when you put back V, how many colors are forbidden? At most 3. In this specific example that I have, exactly 3. But so there's still at least one color left behind, so you can color it using that color. So done. So this is an easy case. So the case when D is equal to 4, the degree is equal to 4. Okay, so let's take a look at that. So here we have vertex V. Let me try and draw cleanly some 4 edges. Here's 1, here's 2, here's 3, here's 4. Okay, good. So once again, the step 1 remains the same. Delete V, delete all these edges. Again, use induction to step A and B remain the same. Use induction to color the rest of the graph, whatever is there. Something like this will be there, right? Some edges over here, some edges over here, some edges here, etc. Yeah, something is there. So now what are you going to do? It depends. If, let's say, once again, somehow in this coloring that you did by induction, only at most 3 colors were used on all the vertices which are adjacent to V. Then again, one color is left over, so you can color V using that color. Right? So far so good. Just let me know if
Yes.
making
Yes.
sense. Yeah. Yeah. Okay. So that case, let us eliminate. Let's suppose that it's not true that less than 4 colors are used on all the 4 edges. So all 4 colors have to be used. So suppose this guy is red, suppose this guy is blue, suppose this guy is green, and suppose this guy is yellow. So with this coloring, now V is in trouble. We have to make a change somehow to the coloring that we did by induction. So here's how we're going to do that. This is the notion of Kemp chain. Okay. So what we're going to do is, let me give labels to these vertices, but I'll give them labels as their as x1, x2, x3, x4. Okay, x1, x2, x3, x4. Okay. So now here's what I'm going to do. I'm going to look at the, what should I call it? Look at the subgraph of G. I hope when I say subgraph, you understand what I'm trying to say. Look at the subgraph of G consisting of, let me change that again. Look at the connected subgraph of G consisting of those vertices colored blue or yellow only. And connected means what? Connected to and containing this one, the vertex x2. That is, you start at x2. Okay, here's what I'm going to do. This is a really formal way of putting it. Here's what I'm going to do. Start at x2. Then go along all possible paths via vertices which are colored either blue or yellow, but not red or green. Okay, so I want you to start at x2 and keep branching out and seeing which all vertices are there which are colored either blue or yellow, and include all of them. Okay, and whatever graph you get out of this, that is this connected subgraph. Let's give it a name. Let's call it H. Let's call it H. Okay, this connected subgraph, we'll call it H. Does it make sense? What graph I'm looking at? So let's say maybe.
Can you explain it again?
Yeah, so here is the vertex which is colored blue. Maybe it has some 3 edges which are incident to it, and they are colored red, green and yellow. Or why different? Red, green and red. Let's say. Okay, red, yellow and red. Then maybe this yellow vertex. So this yellow vertex is what I'm going to pick. Then I'm going to, let's say, consider maybe it's adjacent to, maybe this fellow is adjacent to 1, 2, 3, 4, some other 4 guys, and all of them have different colors. So let's say this is blue, let's say this is blue, let's say this is green. So in this way, I'm going to look at all possible chains, and I'm going to look at the maximal subgraph consisting of all those vertices consisting of only blues and yellows. So it will contain this, it will contain this, it will contain this, and many other guys also. I do not know which other guys, but just look at all those blue yellow fellows only.
Okay.
Okay, containing x2 in particular.
Okay.
Okay, starting at x2, look at only those fellows which are colored blue and yellow. Now there are 2 cases. Either when I look at this continuous chain, somehow there is some way in which joining, you end up with this fellow x4 also being included in the same chain. It's possible. It's possible that there is a path from x2 to x4 consisting only of blues and yellows. Possible.
I'm not sure.
Possible. We do not know. It will depend on the specific graph that we pick, specific coloring that we pick.
So it might not be possible also.
Not be possible also. So we'll consider the only thing to do is consider both cases. That's the only thing we can do. So first case, there is no path between x2 and x4 consisting only of blues and yellows. Okay, so that's going to be case 1. Let me write this down. And this is really the heart of this Kemp chain argument, and this is something worth knowing. Okay, so case, I already used case 1, case 2 somewhere. No, so this is sub case. So sub case 1. This x4 does not belong to H. Okay, where am I? x4 is not in this subgraph consisting of blues and yellows starting from x2. Okay, but if that is the case, then just look at this. What are all the edges between H between those vertices which are in H and those vertices which are not in H. They must be edges between vertices colored either blue or yellow with vertices colored either red or green.
Yes.
Right? Because if there is an edge between a vertex in H with something which is not in H, such that both of them, the one which is not in H is also colored either blue or yellow, then actually by my definition of H, that guy should also have been inside H only, because there's an edge between a guy colored either blue or yellow with some guy also colored either blue or yellow. Right? So the
Right.
only edges between guys in H with guys not in H is between blue yellow fellows and red green fellows. But
Okay.
this gives a very interesting idea, and that is, if this is the case, swap blue with yellow and yellow with blue and vice versa inside H. Does that make sense? Okay. All you're going to do now is you're going to recolor H. Wherever there was a blue, put a yellow. Wherever there was yellow, put a blue. And there is no problem with this. Okay.
Okay.
There's absolutely no problem with this,
No problem. Okay.
because internally, no problem. Externally also no problem, because the edges are between blue yellow guys with red green guys. So there is no problem at all. So what is the ultimate result of doing this? The ultimate result is you have a red here, you have a green here, you have a yellow here, but you also now have a yellow over here. That is, are you able to see my cursor? I'm just moving it around. You have a, you have red here, green here, yellow here, and yellow here as well.
Okay.
So now blue is free. You can color V using blue.
Okay. Okay.
That is the genius. Okay.
Okay.
By swapping blue and yellow inside H, you have now freed up the color blue, and now you can color V using blue. So four coloring has been found.
I
That is in this subcase, the specific subcase that there is no chain between, there is no Kemp chain between X2 and X4. So now you know what a Kemp chain is, right? So there's no Kemp chain between X2 and X4, you know what to do. What if there is a Kemp chain between X2 and X4? Then doing the swapping business is not going to help, because this blue will become yellow and this yellow will become blue. Still you have four colors. So what to do? So if you have a Kemp chain, the smart idea is, now look at a Kemp chain between red and green, between X1 and X3. Let me draw a newer diagram, because this diagram has become quite messy. So subcase 2, X4 is in H. Okay, so that is to say you have a vertex V here, you have this guy, this guy, this guy, this guy, right? And we gave them these colors, right? X1, X2, X3, X4. Oops, X2, X3, X4. Where are we? This was red, this was green, this was blue, this was yellow, and there was, we claim, we means we are in the, under the hypothesis there is some path, Kemp chain
X4.
from
Okay.
X2 to X4. Okay.
Ah.
So now I'm saying, okay, this is no good. This Kemp chain we have between X2 and X4 makes it no good. So let's swap our point of view and look at Kemp chains from X1 to X3. Okay, that is to say, let's say we start at X3. Start at X3 and look at the connected subgraph containing X3, consisting of all those vertices which are colored only red and green.
Okay.
So this is some other graph. Let's call it H prime or something like that. So this is a new graph H prime. Again, there are two cases. Either H prime contains X1 or it doesn't contain X1. If H prime doesn't contain X1, you know what to do. Inside H prime, just swap red and green. Then you will free up green and you can color V using green.
Okay.
Same argument. But so now the final case, that what if the Kemp chain contains X3 and X1? And this is impossible, because simply by the geometry of the plane. So far I've not done anything which really is so involved with the geometry of the plane. I'm only using that there's a vertex of degree less than, vertex of degree 5. But you can find vertices of degree 5 anywhere. No, I mean, that is not really so special. But here is where the geometry of the plane comes into the picture. We know there is a Kemp chain between X2 and X4, which means vertices consisting only of blues and yellows. Okay. Can there be a Kemp chain consisting only of reds and greens like this? No, it has to cut across, right? How can it cut across? The only way it can cut across is if it either passes through a vertex. So there's some vertex here, and a vertex here. So it has to cut across like this, which means this is not a planar graph because there's a crossing, or there is a vertex which is common to both chains, which means it belongs to the blue yellow chain and the red green chain, but that is not possible. So both possibilities are not there. So if the blue yellow chain doesn't work, the green red chain will work. This is the argument. Does this make sense? You want me to go over it again? I can go over it again.
No, got the point. So it's kind of a geometry problem.
Yeah, absolutely. Right. So this is the argument of Kemp chains. This was for the case degree of V is equal to 4. Okay. So now there's one more case to handle. Degree of V is equal to 5. It will be very simple. I'll just tell you the two. There are only two ways to handle degree of V is equal to 5. No, it's very easy. So let me just quickly show you the diagram that you have to keep in mind, and then you can try it for yourself, and then you will have proved the Four-Colour Theorem. Okay. So the last case is degree of V is equal to 5. So we saw in degree of V is less than 4, no problem, and it's equal to 4, Kemp chains, and it's equal to 5. What kind of status is possible? Let's see, 1, 2, 3, 4, 5, right? So there are two possibilities. I'll just draw two of these guys. 1, 2, 3, 4, 5. Yeah, good. So again, if by what I want to do, delete this vertex V, by induction color everything else, right? And once you color everything else, you check whether how many colors are used in the neighbors of V. If less than 4 colors are used in the neighbors of V, then you're anyway done, because whatever the leftover color is, you can use that to color V and you're done. So let's always assume that all 4 colors are used in the induction hypothesis, via the induction hypothesis, in coloring all the neighbors of V. So if all 4 colors are used, up to some relabeling of the colors, what I'm calling red, maybe you will call blue, things like that. So up to relabeling, the configuration of the colors can only be in 2 possibilities. It is red, blue, red, green, yellow, or red, blue, green, yellow. Do you see the difference? What's the difference between the two configurations? Do you see it? So this is, let's say, config 1. This is config 2. The difference is whether the two vertices with the same color, whether two vertices with the same color are adjacent or not adjacent.
Diagonal. Okay.
It's not about diagonal or not diagonal. It means I could draw it, all of them bunched together and all that. It's more like, are they adjacent or are they not adjacent? Adjacent in what sense? In this, if I count the colors, let's say in sequence counterclockwise or clockwise, pick some orientation. The fact that you can do this with some orientation in mind is an inherent property of the plane. Okay, that you can move around the plane in an oriented fashion is a property of the plane. So that's what we're using over here. So it's either like this or like this. Okay, fine. Good. So what can we do? So among these two, configuration 2 is easier to handle because I want you to use the same Kemp chain argument. Okay, I want you to use the same Kemp chain argument for which two? For blue, yellow, and then for red, green. Handle, okay, using the same Kemp chain argument.
Kemp chain argument, okay.
Just write down the same argument and see. Consider the Kemp chain starting from here with blue and the yellows. If it's not going there, swap. If it's going there, consider red, green. Okay. So red, green could either be this or both, whatever. Multiple options are possible, but
okay.
In either scenario, it is not possible because you will never find a Kemp chain going from here all the way into here, thanks to the existence of a blue-yellow Kemp chain. So configuration 2, you can handle using the same Kemp chain argument. See that the same thing cannot happen in configuration 1 because suppose you do the blue-yellow business. Okay, blue, yellow. You say that, okay, if there's no chem chain, done. So if there's a chem chain, look for red, green. So this red, green will not exist. But what about this red, green?
But
It's possible, no?
that will exist.
So then again, you're in trouble, because if you swap in this chem chain between red and green, again you'll be having with green and red. So Kemp comes up with a very interesting idea, which is to use two chem chains at the same time. Okay, so you look at blue yellow. If it works, great. If it doesn't work, you have a blue yellow chem chain. Look at blue green. Blue yellow doesn't work. Look at blue green. Okay.
Okay.
If blue green works, again you are done. So assume blue green also doesn't work. So you have a chem chain like this blue yellow, blue yellow. You have a chem chain like this blue green. Now what shall we do? Now look at red green and red yellow. Okay.
Okay.
Can you find a red green chem chain? Chem chain connecting x1 to x4 consisting of reds and greens. Well, this guy is bounded by a blue yellow chem chain. So it's not possible to get a red green chem chain like this. Can you find a red yellow chem chain? Well, this is bounded by a blue green chem chain, so you can't find a red yellow chem chain like this. Right? Does it make sense?
Makes sense.
So all you have to do is swap red with green over here on the chem chain starting at x1. Swap red with yellow on the chem chain starting at x3. And then what you'll have done is you will have gotten blue, yellow, yellow, green, green. So red will have become free. So then you color V using red.
So just repeat. Can you repeat that once?
In configuration 1, you see whether a blue yellow chem chain exists or does not exist. If there is no blue yellow chem chain, you're done. So assume there is a blue yellow chem chain. Then you check blue green. If there is no blue green chem chain, you're done. So assume there is a blue green chem chain. So now there's a blue yellow chem chain and a blue green chem chain.
Then
now
that one is impossible.
Red green and red yellow. So you look at red green and red yellow. There cannot be a red green chem chain because it has to pass through the blue yellow one. There cannot be a red yellow chem chain, so it has to pass through the blue green one. So in whatever the chain is over here and whatever the chain is over here, swap between the colors there, red and green. Yeah, swap between red and green here. Swap between, I don't know whether you can see when I say here. Swap between red and green here. Swap between red and yellow here. Then you'll have blue, green, yellow, green, yellow. So red is free. Both reds are gone. So now you color V using red. That's the geometric argument. Yeah, just take a look at this diagram for some more time if you want.
So which one color to swap for the last argument?
Let me tell you. Let me just. So over here, we're going to look at RG chains, red green chains. Here we're going to look at R yellow chains, red yellow chains. So you swap those two colors here, swap those two colors here. Because this chain cannot reach all the way till x4, starting at x1, thanks to the existence of a blue yellow chem chain. This one at x3
so
cannot
we are
reach
converting configuration 1 to configuration 2.
No. We are to a very different configuration. One, it contains. See, if you convert, no. So if you convert it like that, see, it's going to become like this. It's going to look like blue, green. How do I put this one? Blue, green, yellow, green, yellow.
Okay. So it's not configuration 2. Okay.
No. You have to do both. You have to do both.
Both.
Then only red will vanish, and then only you'll get red free at V. So it'll become blue, green, yellow. Where is the red? Red is free. So you color V
Free.
using red.
Okay. Got it.
Got it? Excellent. So now you also know the proof of four-color theorem. Shabash.
Thank you.
Except that it's wrong. So now I need you to tell me why it is wrong.
Yeah.
Okay, I convinced all of you.
Okay. I got convinced.
Yes, sir.
Very good. Kemp also convinced everyone. He became fellow of Royal Society man using this proof.
Okay.
So you have to think about it and tell me what is wrong with this proof. This is not a proof of the four-color theorem. It has to be wrong. Okay.
Okay. So just some hint. I think I can.
Draw some pictures. Draw some pictures and see how.
Pictures. It's problem. The wrong. The chains are wrong. I think the Kemp chains.
See what kind of chains you can come up with. So you start with this configuration 2, which is or configuration 1, with the vertex V having 5 vertices. And
So the fifth one have a problem.
You tell me, were you convinced? Where are you not convinced? You tell me. Are you convinced at degree 4, degree 5, configuration 1, configuration 2, whichever is not convincing for you. I will not give any hint beyond this. You take whatever is not convincing for you, draw that configuration and see what kind of complicated chains you can make, how you can somehow, fit together a pattern in some way such that there is some subtlety over here. There is some subtlety over here. Just see. It's an instructive exercise. Okay. Yeah. But if you're all convinced that the four-color theorem is true, that this proof is fine, then Kemp is probably happy wherever he is. X3 red, X4 green, X3, X4 chain exists. X3 red, X4 green. I'm saying you have to once again. Which one? Something's wrong. X3 red, X4 green. Then an X3, X4 chain exists. How red is free? I don't understand, Jitesh. Maybe you'll have to unmute yourself. I can share my screen once more if you like. Then you can ask me exactly what part is not confusing, what part is not convincing. Here we are. Which configuration?
Can we connect X3 and X4?
Can we connect X3 and X4? You're asking?
Yes, sir. Then I guess X3 red is not true.
Yeah, it's possible. I'm not saying pick a red-green chain between X3 to X4. I'm saying start at X1, look at the connected component consisting of only red and green vertices. That one is not going to be connected to X4. One connected to X1 with red greens is not going to be connected to X4. X3 may be connected to X4. I don't really mind. Sure, it's possible. But that's why I'm choosing very specifically the opposite guys. I want to choose X1 with X4, X3 with X5. I don't want to pick the adjacent guys. Does that help?
Yes, sir.
Kind of a little bit. Okay, no problem. Yeah, so that's it. That is.
So swapping has some problems. So if there is some problem in swapping.
That's the only thing you're doing. The only operation you're doing is swapping. So obviously some problem has to be there.
No, I'm just checking if can you tell, sir, is there any problem in swapping? No.
See, there is only one operation you're doing, which is to identify a chain which you want to swap.
And swap. Okay.
So if there is a problem, obviously there's a problem in swapping. See, it's like this. Just because I'm saying Kemp's proof is wrong, just because many great people have said Kemp's proof is wrong, doesn't mean you should believe that Kemp's proof is wrong. If you are convinced that Kemp's proof is right, make this argument rigorous and show. Okay. All these diagrams that I'm drawing, etc., make it rigorous. like as rigorous as you can. Don't go looking for a flaw if you want. Go looking for a rigorous proof. Then automatically the flaw will come out. Okay.
Okay.
Just try. Just spend some time on it. No problem. There is no hurry.
I'll try. I'll try.
If you want, we can do part 2, part 3 of the same talk. I can tell you next time we meet, I will tell you about Tate's incorrect proof. Then you can tell me what is wrong with that also.
Would love to do that, sir.
Yeah, sure. Sir, a great thanks for coming here in the club. We are very thankful for this. We really enjoyed your presence in the club. It was really amazing, and I hope everybody would join the meet have felt this amazing. For the freshers, it would really be the real introduction of the club because we haven't seen such interactive activity before. We thank you for taking out your precious time and giving that to us. We really learned the four-color theorem today.
I don't say that. Huh? You did not run the Four-Colour Theorem today.
Okay.
Yeah, thank you very much for inviting me. It's always a pleasure to be back in the math club. So something that was very close to my heart when I was there. And I always enjoyed interacting, especially with my juniors when I was over there. I also learned a lot from my seniors and something that I also like to pass on as much as I can. And yeah, we should do this maybe once after COVID is gone. We should probably do some. If I can drop by, I said, well, we should do it a live one. Otherwise, as much of this charm goes away. You want to go to the board and use colored chalk and actually do something with it. Now it's not possible. You have to tell me, sir, x3, x4. Then I have to open the whiteboard. It's not fun, no? Anyway, let's see. It was supposed to be 1 hour. I took, I think, over nearly 2 hours. I'm very sorry about overshooting, but such is the nature. Once you start talking,
No, sir, it's amazing. No problem.
Actually, you know what? When I said four-color theorem, I had so much to talk about. I was thinking, okay, I'll tell you. I'll start with the history. I'll tell you about Kempis proof. Then I'll tell you how Kempis proof was wrong. Then I'll tell you about Tate's proof. I'll tell you how Tate's proof was wrong. Then I'll tell you about how he found out a wrong, that it's wrong. How he generalized it to higher dimensions. Then about Heesh's technique for discharging, which was very crucial in proving in whatever Apple and Hacken did in the final thing. The discharging method is another really beautiful thing. Then I wanted to talk about so many stuffs. And even generalizing four-color theorem itself in many dimensions. You can generalize it to higher surfaces, graphs on higher surfaces. You can generalize the coloring itself to things that I studied, list coloring problems, things like that. So much to talk about. But then I thought, एक घंटा है पागल हो जाएंगे लोग अगर ऐसे करेंगे तो. So I decided no slides. I will not prepare anything. We just go as slowly as we can so that everyone gets one thing. And today the one thing if you would have got is some certain key concepts. One is what a chem chain is and what it does. Another is really this very useful notion that if you take an average and you have a bound that the average is less than a quantity, then there must be some guy who is less than the quantity. Cannot tell you how important this very simple concept is. So take these and in your spare time, draw some chem chains, see where it is going wrong. This proof that I gave you today, it's not a proof. It's wrong.
Okay, sir.
Okay, Devash.
It was a good
Thank you.
Yeah. Okay, sir.
Yeah. Good. Thanks, Devashish.
Yeah, thank you again, sir. Okay.
Yeah, thank you to everyone who came also, and hope you all enjoyed.
Thank you, sir.
Yeah.
Thank you, sir.
Sure.